Welcome to this problem walkthrough. Today, we'll explore problem number 336, titled Palindrome Pairs. This is an exciting problem that challenges us to find pairs of words that, when concatenated, form palindromes. It's an excellent practice for honing your string manipulation and algorithm design skills. Let's dive in. The problem asks us to find all pairs of distinct indices in a given list of unique words, such that when we concatenate the words at those indices, the resulting string is a palindrome. A palindrome, as you might recall, is a string that reads the same forwards and backwards, like madam or race car. For the input, we are provided with a list of strings called words. The output should be a list of index pairs that satisfy the palindrome condition, where each pair is distinct and represented as I, J, in a zero-based index format. To understand this better, let's take a look at some examples. In the first example, the input list is ABCD, DBA, LLS, this, SSSLL. The output is 0, 1, 1, 0, 3, 2, 2, 4. Here's why: when we concatenate ABCD and DBA, the result is ABCDDCBA, which is a palindrome. Similarly, concatenating DBA and ABCD produces DBAPT, another palindrome. Looking further, GS and LLS combine to form SLLS, and LLS with SSSLL gives LLS-SSSLL, both of which are palindromes. These pairs of indices are added to the output since they satisfy the condition. In the second example, the input list is BAT, TAB, CAT. The output is 0, 1, 1, 0. This is because concatenating BAT and TAB gives BAT-TAB, which is a palindrome, and reversing the order TAB and BAT results in TAB-BAT, another palindrome. However, CAT does not form a palindrome with any other word in the list, so it does not contribute to the output. In the third example, the input list is A. The output is 0, 1, 1, 0. Here, the empty string acts as a neutral element, such that concatenating and results in a palindrome. Similarly, and I'll also form a, making both index pairs valid. The constraints and edge cases highlight some important considerations. Each word in the list consists of lowercase English letters, and the list can contain up to 5,000 words, with each word being as long as 300 characters. This means the solution must be highly efficient to handle such large inputs. Edge cases include the presence of an empty string, which can pair with any string to form a palindrome. Words of length 1 are always palindromes, so they can combine with the empty string or their reverse. It's also important to ensure no duplicate index pairs are returned. Lastly, if one word is the reverse of another, their concatenation will always be a palindrome. These details will guide the development of an optimal solution. To solve the palindrome pairs problem, one straightforward approach is the brute force method. Here, we consider all possible pairs of indices, I, J, where I is not equal to J. For each pair, we concatenate the two words, I, and words, J, and then check if the resulting string is a palindrome. The key to this check is observing that a palindrome reads the same backward as forward, so we simply reverse the concatenated string and compare it to the original. While this method is simple and directly solves the problem, it has significant drawbacks in terms of efficiency. For a list of n words, each with an average length of k, we would need to check O, n squared, pairs, and verifying each palindrome takes O, k, time. This results in an overall time complexity of O, n squared asterisk k, which grows quickly as the input size increases, making it impractical for larger datasets. This trade-off highlights the need for a more efficient solution. To address the inefficiencies of the brute force method, we can use an optimized approach that leverages hashing. This method reduces redundant computations by focusing on the unique properties of palindromes. Specifically, we consider that a concatenation of two words, I, plus words, J, forms a palindrome if certain conditions are met. First, either the prefix of the concatenated string is a palindrome, and the reversed suffix exists in our word list. Or, the suffix is a palindrome, and the reversed prefix exists in the list. To achieve this efficiently, we use a hash map to store the reverse of each word along with its index, allowing for quick lookups. The algorithm then involves splitting each word into all possible prefix and suffix combinations. For each split, we check whether the conditions for forming a palindrome are satisfied using the hash map. Additionally, we ensure that a word is not paired with itself by comparing the indices. This approach strategically minimizes unnecessary checks while focusing only on valid palindrome pairs. The time complexity of this optimized approach is significantly improved compared to brute force. For each word, we process its prefixes and suffixes in O(k) time, and since there are n words, the overall complexity is O(n*k squared). While this is slightly more complex to implement than the brute force method, it offers a significant speedup for larger input sizes by avoiding the quadratic growth of pairwise checks. Another alternative to consider is the tree-based approach, which involves storing words in a tree structure to efficiently find matching prefixes or suffixes. However, this method introduces additional complexity in constructing and traversing the tree, and for this specific problem, the hashing approach tends to be faster overall. While tries are useful for many string matching problems, their overhead often outweighs their benefits here, especially when compared to the simplicity and efficiency of the hashing strategy. After evaluating the different approaches, we chose the optimized hashing strategy as the best solution for this problem. This method strikes a balance between efficiency and simplicity. It avoids the quadratic time complexity of the brute force approach by eliminating redundant computations, while still being straightforward to implement and debug compared to the tree-based method. By focusing on the properties of palindromes and leveraging hash maps for quick lookups, this approach minimizes unnecessary work and handles larger inputs effectively. Its overall time complexity of O(n*k squared is a significant improvement over the brute force method's O(n²k). This makes the hashing strategy both practical and performant, offering a robust solution to the palindrome pairs problem. To solve the problem of finding all unique pairs of indices where the concatenation of two words forms a palindrome, we can start with a straightforward brute force approach. First, we generate all possible pairs of indices using two nested loops. The outer loop iterates over each word in the list, while the inner loop iterates over the remaining words. This ensures that every combination of words, I, plus words, j, is evaluated. For each pair, we concatenate the two words and check if the result is a palindrome. This check involves reversing the concatenated string and comparing it to the original. If the strings match, it confirms that the concatenated result reads the same forward and backward, making it a palindrome. We then store the valid pairs in a result list. After processing all pairs, the list of valid index pairs is returned as the output. While this approach is simple and gets the job done, it involves a lot of redundant checks, which makes it inefficient for larger inputs. The brute force method is computationally expensive due to its nested loops. Generating all pairs takes O(n²) time, where n is the number of words, and checking if a string is a palindrome adds an additional O(k), where k is the length of the concatenated string. In the worst case, this results in an overall time complexity of O(n²*k). To address this inefficiency, we can employ an optimized approach using hashing. A key insight here is that palindromes exhibit certain predictable patterns. For instance, if a string s is paired with its reverse s_rev, the result is always a palindrome. Using this observation, we can leverage a hash table to store reversed words and their indices. With this setup, we can efficiently check for valid palindrome pairs without generating all possible combinations. Additionally, by splitting words into prefixes and suffixes, we can identify cases where only part of the word contributes to the palindrome, further reducing redundant computations. To implement the optimized approach, we first construct a hash map where the keys are the reversed strings and the values are their indices in the input list. This allows us to quickly retrieve the index of a reversed word. Next, we iterate through each word in the list and split it into all possible prefixes and suffixes. From here, several cases are checked. In the first case, if the reverse of the entire word exists in the hash map and it's not the same word, we record the pair. In the second case, we examine all possible prefixes of the word. If a prefix is a palindrome and the reverse of the corresponding suffix exists in the hash map, this forms a valid pair. Similarly, for the third case, we look at the suffixes. If a suffix is a palindrome and the reverse of the corresponding prefix exists, we add this pair as well. Throughout this process, we use a set to store the results, ensuring that duplicate pairs are avoided. Finally, we convert the set into a list and return it as the output. This optimized approach relies on key insights about palindrome properties. By breaking words into prefixes and suffixes, we can efficiently identify potential matches using the hash map. The hash map itself plays a crucial role in enabling fast lookups for reverse strings, while the set ensures that we avoid duplicate pairs. It's important to handle edge cases carefully, such as empty strings, single-character words, and duplicate entries, as these can introduce additional valid combinations that need to be accounted for. From a complexity perspective, building the hash map takes O, and *k, time, where n is the number of words and k is the average length of the words. Checking prefixes and suffixes involves splitting each word into up to k parts, with palindrome checks for each split taking O, k, leading to an overall time complexity of O, and *k squared. The space complexity is O, and *k, primarily for storing the hash map. This approach strikes a balance between efficiency and comprehensiveness, making it well suited for solving the problem at scale. The provided solution efficiently identifies all unique index pairs such that the concatenation of the strings at those indices forms a palindrome. Here's a breakdown of the implementation. 1. Helper function. The is_palindrome function checks if a given string is a palindrome by comparing it to its reverse. This is a utility function used repeatedly in the main logic. 2. Word dictionary. A dictionary word_dict is created to map each word to its index in the input list. This allows for O1 lookups to find the index of any reversed string during the process. 3. Iterating through words. The main loop iterates over each word in the input list. For each word, the function splits it into all possible prefix and suffix combinations by iterating through its length. For checking prefix palindromes, if the prefix is a palindrome, the function checks if the reverse of the suffix exists in word_dict. If so, it implies that the reversed suffix combined with the current word forms a palindrome. 5. Checking suffix palindromes. Similarly, if the suffix is a palindrome, the function checks if the reverse of the prefix exists in word_dict. This ensures that the palindrome is identified when the concatenation happens in the opposite order. 6. Avoiding duplicates. The condition word_dict, reversed_suffix, = I ensures that a word is not paired with itself. This prevents duplicate or invalid results. 7. Results list. The valid palindrome pairs are appended as index 1, index 2 to the results list. 8. Final return. After processing all words, the function returns the results list containing all unique palindrome pairs. This implementation is efficient, leveraging dictionary lookups to avoid the need for nested loops over all word pairs, making it suitable for larger datasets. The complexity is determined by the number of words and their lengths, with the palindrome checks and string slicing being optimized for performance. Here, we start by importing the necessary Java utilities and defining the solution class. Inside, we implement the palindrome pairs method, which will return a list of all valid palindrome pairs from the given array of words. To begin, we define a helper method called isPalindrome to check if a given string is a palindrome. This method compares characters from the beginning and end of the string, moving inward, and returns false if any mismatch occurs. If no mismatches are found, it returns true. Next, we initialize a hash map called wordMap to store each word and its index for quick lookups. We also create an empty list called results to store the output pairs. Then, we iterate over the array of words, adding each word and its index to the map. This setup allows us to efficiently check for palindrome pairs later. Now, we start iterating through the words again, accessing each word by its index to begin searching for valid pairs. For each word, we divide it into two parts, the prefix and the suffix. This is done by taking substrings from the beginning up to the current position and from the current position to the end. First, we check if the prefix is a palindrome. If it is, we reverse the suffix and check if the reversed suffix exists in the map. If it does, and its index is not the same as the current word, we add the pair of indices to the results list, with the reversed suffix coming first. Next, we check if the suffix is a palindrome. To avoid duplicates, we ensure this check only runs when the current position is not the end of the word. If the suffix is a palindrome, we reverse the prefix and look for it in the map. If found, and it's not the same word, we add the indices to the results list, this time with the current word coming first. After iterating through all possible splits and performing these checks, the method returns the results list containing all valid palindrome pairs. To solve the problem of finding palindrome pairs, we start by initializing two data structures. First, we create a dictionary called word_dict that maps each word in the input array to its index. For the given example, words equals bat, tab, cat, the dictionary becomes bat 0, tab 1, cat 2. This allows us to quickly look up the index of any word or its reverse. Next, we initialize an empty list called results to store the indices of any valid palindrome pairs we identify during the process. Once these structures are in place, we loop through each word in the input. For the first word, bat at index 0, we split it into all possible prefixes and suffixes by iterating over its length. For instance, when the split is at j equals 0, the prefix is an empty string and the suffix is bat. We check if the prefix is a palindrome, which it is since it's empty. Then, we reverse the suffix to get tab, and since tab exists in the dictionary at index 1, we add the pair 1, 0 to the results list. Continuing, when j equals 1, the prefix becomes b and the suffix is at. Here, the prefix is also a palindrome, but reversing the suffix gives ta, which does not exist in the dictionary, so no pair is added for this split so far. Now we move to the next split of bat at j equals 2, where the prefix is ba and the suffix is t. Since t is a palindrome, we check the reverse of the prefix, which is ub. However, ub is not in the dictionary, so no pair is added. Finally, for j equals 3, the prefix becomes bat and the suffix is empty. Here, the suffix is a palindrome, and reversing the prefix gives tab, which exists in the dictionary at index 1. This allows us to add the pair 0, 1. Moving on to the second word, tab at index 1, similar splits and checks reveal the same pairs, 0, 1, and 1, 0, as valid palindrome pairs. Lastly, for the word cat at index 2, none of the splits produce a valid palindrome pair, so no new pairs are added. This concludes the processing of the first example, and the final output for this input is 1, 0, 0, 1. In the second example, the input words are words equals ABCD, BA, LLS, S, SSSLL. Just like before, we start by initializing the word_dict with mappings ABCD 0, BA 1, LLS 2, S 3, SSSLL 4, and an empty results list to store our results. For the first word, ABCD at index 0, we go through all possible splits and find two valid pairs, 1, 0, and 0, 1. These pairs are formed because ABCD and its reversed BA are both present in the dictionary. Moving on to the third word, LLS at index 2, we again perform the splitting process and identify the valid pair, 3, 2. This pair is valid because the suffix s is a palindrome, and the reverse of the prefix ll exists in the dictionary at index 3. Next, we process the fifth word, SSSLL at index 4. By splitting and checking for palindromes, we find one valid pair, 2, 4. Here, the suffix ll is a palindrome, and the reverse of the prefix SSS exists in the dictionary at index 2. After completing all iterations for this example, the final output of results is 1, 0, 0, 1, 3, 2, 2, 4. Moving on to the third and final example, the input words are words equals a. As usual, we initialize the word_dict as a, 0, 1, and the results list as empty. In this case, the empty string plays a critical role since it can form a palindrome with any other word. For the word a at index 0, we split it at j equals 0 into a prefix of an empty string and a suffix of a. The prefix is a palindrome, and reversing the suffix gives a, which exists in the dictionary at index 0. Then, splitting at j equals 1 gives a prefix of a and a suffix of an empty string. The suffix is a palindrome, and reversing the prefix gives a, which also exists in the dictionary. These checks allow us to add the pairs 1, 0, and 0, 1 to the results. After completing the iterations, the final output for this example is 1, 0, 0, 1. Here, we analyze the time complexity of the solution. The goal is to identify all pairs of indices where concatenating the words forms a palindrome. To start, we build a dictionary that maps each word to its index. Since we iterate through all n words and each word has an average length of k, constructing this dictionary takes (k) time. Next, the outer loop processes each of the n words individually, which translates to n iterations. Within each iteration, we split the word into all possible prefix-suffix pairs. For a word of length k, there are k plus 1 possible splits, so the inner loop runs O, k, times for each word. These steps are the foundation of how the solution iterates through the input efficiently. Now, let's consider the palindrome checks and dictionary lookups. To verify if a string is a palindrome, we compare it against its reverse, which requires O, k, time for a string of length k. This operation is performed for both the prefix and the suffix during each split, so there are O, k, palindrome checks per split. Additionally, we perform dictionary lookups to check for the reversed prefix and suffix, which are O, 1, on average. Combining these steps, the total work for each word involves O, k, splits, and for each split, we perform O, k, palindrome checks and O, 1, lookups. This results in O, k squared, operations per word. Since there are n words, the total time complexity becomes O, n asterisk k squared. In the best case, where words are very short, the complexity reduces to O, n. However, in the worst case, with long words and no optimization, the complexity reaches O, n asterisk k squared. Turning to space complexity, we account for different components. The primary contributor is the word dictionary, which stores n words as keys and their indices as values. This requires O, n asterisk k, space, as each word has an average length of k. Additionally, temporary variables like the prefix, suffix, and their reversed counterparts occupy O, k, space per word during computation, but these are reused and do not add to the asymptotic complexity. Lastly, the results list stores all valid palindrome pairs. In the worst case, if every word forms a pair with every other word, we could have O, n squared, pairs, each requiring constant space to store. Combining these, the total space complexity is O, n asterisk k, for the dictionary and O, n squared, for the result storage. In the worst case, this is dominated by O, n squared. Finally, let's compare this solution to a brute force approach. A naive method would involve iterating through all O, n squared, word pairs and checking if their concatenation forms a palindrome, which takes O, k, time per pair. This results in a total time complexity of O, n squared asterisk k. The given solution significantly improves on this by avoiding unnecessary concatenations and instead using dictionary lookups and optimized palindrome checks, achieving O, n asterisk k squared. Mathematically, this arises from the outer loop running O, n, times, the inner loop performing O, k, splits, and O, k, work being done per split. Over all n words, this totals O, n asterisk k squared. For space complexity, the dictionary and results list dominate, requiring O, n times k plus n squared, space. This efficient use of time and space highlights the advantages of the optimized approach over brute force. When solving the palindrome pairs problem, there are some common mistakes to be aware of. First, it's easy to forget that empty strings need special handling. Since a palindrome reads the same forward and backward, concatenating an empty string to a palindrome still results in a valid palindrome. This means you need to account for cases where one of the words in your list is an empty string. Additionally, single-character words are always palindromes by definition, so if you ignore these, you might miss valid pairs. Another frequent oversight is the order of concatenation. Remember, combining words I with words J is not the same as combining words J with words I, so you must check both orders to ensure no valid pairs are skipped. On top of that, relying on a brute force solution can be problematic for large inputs. The naive approach has a time complexity of O, n squared asterisk k, which becomes impractical as the dataset grows. Finally, many solutions fail to consider reversed substrings. Palindrome pairs often form when a word's prefix or suffix matches the reverse of another word, so ignoring this pattern can lead to missing valid results. When preparing for interviews, it's important to keep a few key insights in mind for the palindrome pairs problem. While brute force solutions are useful for demonstrating your understanding of the problem, interviewers will typically expect an optimized approach. Using a hash map or a tree data structure can store reversed words for fast lookups, making your solution significantly more efficient. Additionally, focusing on edge cases is crucial. Be sure to test scenarios like empty strings, single-character words, and words that are already palindromes, and explain your reasoning clearly during the interview. If you choose to begin with a brute force approach, make sure to discuss its inefficiencies and explain how a hash-based approach can improve lookup time to O, n asterisk k, where k is the average word length. Finally, clear communication is key. Highlight insights such as how reversing a word or analyzing its prefixes and suffixes can help identify palindrome pairs efficiently. This demonstrates not only your problem-solving skills but also your ability to think critically about trade-offs. The palindrome pairs problem is closely related to several other challenges that you may encounter, such as LeetCode 5, which focuses on finding the longest palindromic substring, LeetCode 266, which covers palindrome permutations, and LeetCode 131, which involves palindrome partitioning. Exploring these problems can deepen your understanding of palindromes and their variations in computational contexts. Additionally, there are alternative approaches to solving the palindrome pairs problem. One common method is the hash map approach, where you store the reverse of each word in a hash map. This allows for quick lookups and facilitates checking prefixes and suffixes for potential palindrome pairs. The trade-off here is that while this approach reduces time complexity to O and *k, it does require extra space for the hash map. Another option is the tree approach, where you insert all words into a tree in reverse order and traverse it to find matching prefixes and suffixes. While this method offers efficient lookups for large datasets, it is more complex to implement and requires careful management of the tree structure. Another approach to consider is the two-pointer technique. This method involves using two pointers to check if a word or its concatenation with another word forms a palindrome. For example, one pointer starts at the beginning of a word and the other at the end, moving toward the center to validate palindrome properties. While the two-pointer technique is often used to verify solutions or test smaller cases, it is not scalable for large inputs. The reason is its time complexity, which remains O and squared *k, making it inefficient compared to hash map or tree-based solutions. However, its simplicity makes it a useful tool for validating results during initial problem-solving stages or for understanding the mechanics of palindromes. When applying this method, always keep the trade-offs in mind and be ready to explain why it might not be the best choice for large datasets in an interview setting. Great job following along. To recap, we tackled the palindrome pairs problem, leveraging string properties and optimization techniques. Remember to practice and refine your skills with similar challenges. Thank you for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!